What if the intricate patterns of life weren't really invented by biology, but were, inherited from the fundamental laws of the universe? What if evolution found a blueprint for building complex things that was already written into the strange language of quantum physics? It's a wild question, and it's at the heart of this mind-bending new idea. And it all starts with a picture you absolutely have to see to believe.
Okay, so look at this. On the left, you're seeing a real microscopic image of mitochondria. Yep, the powerhouses of our cells. Now look at the right. That's a computer simulation of 150 quantum particles, or qubits, just doing their thing over time. The resemblance is, well, it's uncanny, right? And this isn't some coincidence. This crazy visual echo is the jumping-off point for a radical new idea called Divot Theory.
And that really brings us to the core question we're going to dig into. How is it even possible that the purely mathematical world of quantum mechanics is spitting out images that look like they're ripped straight from a biology textbook? The answer, it turns out, suggests a connection between the quantum and biological worlds that's way, way deeper than we ever imagined.
So, how do we get from tiny quantum particles to the structures inside our cells? Well, it all kicked off with this initial observation, a kind of ghost in the machine that researchers just couldn't ignore.
It actually started out pretty simple. Scientists were running these simulations, and they saw that when you just let a bunch of qubits do their own thing, they weren't just bouncing around randomly. Nope, they were self-organizing. They were forming these complex, flowing, branching networks that looked shockingly, well, organic. It was the spontaneous emergence of order out of chaos that just demanded an explanation.
So the key to this whole theory comes down to one simple fundamental concept. If we want to understand the big, complex network, we first have to understand its smallest building block, something they call a divot.
Okay, so in the quantum world, you can map the state of a single particle onto a sphere. It's called the Bloch sphere. As that particle changes and evolves, it traces a path on that sphere's surface. Researchers noticed this path kind of looked like a little depression or a dent, so they called it a divot. You can think of it like the quantum version of a single footprint in the sand.
And here you can see it in action. This is just one particle's journey. It's a simple, elegant little path. By itself, it's not much to look at. But the real magic happens when you stop looking at just one footprint and you start looking at hundreds of them all at once.
Because when you have 100 qubits all tracing their own little divots, something incredible starts to happen. These simple individual paths, they interact, they combine, and they form a complex, collective structure. This is a core idea of self-organization. Really intricate patterns just emerging from simple local rules, with no one in charge.
So we've got particles creating patterns. But what's guiding them? The answer lies in this invisible landscape they're all navigating. And this is the bridge that connects the quantum world to the biological one.
The researchers over at Trinity College Dublin have this fantastic way of describing it. They say the energy environment that these quantum particles live in isn't some smooth, rolling hill. It's more like a rugged terrain of fractured valleys with angular tiles. Just picture a topographical map, but instead of altitude, it's mapping energy. It's got peaks, valleys, and crucially, paths of least resistance.
And here is the absolute knockout punch of the whole idea. Divot theory says that quantum particles organizing themselves and mitochondria organizing inside a cell are, at their core, doing the exact same thing. They are both just trying to find the most efficient setup, the lowest energy points, on a really rugged energy landscape. They're both following the universe's energy map. Now, that is a beautiful idea, but is it actually true? To find out, the researchers ran a ton of simulations, tweaking the rules of their quantum world to see if they could replicate and maybe even optimize this self-organization. And what they found was really fascinating. They tested how the amount of interaction or correlation between the particles affected the quality of the structures they formed. And it turns out, if there was too little interaction or way too much, the organization was pretty poor. But as you can see from that highlighted bar, there was a sweet spot right in the middle, this medium correlation, that produced the most well-defined, coherent clusters.
And that sweet spot, it's got a number, 0.5. You can think of this as the Goldilocks value. Not too hot, not too cold, but just right. It's the perfect balance between order and freedom, letting the system form stable structures without getting totally locked into place. You're going to want to remember this number.
Now, this data table, it reveals another really important clue. The medium correlation experiment didn't just have the best quality score. Look at the number of clusters it formed. 6. Now, that might seem like a totally random detail, but trust me, it's about to become the most important piece of this entire puzzle.
All right, now we get to the heart of it all. This isn't just about some abstract patterns in a computer simulation. This is where that bridge between quantum physics and real biology becomes solid.
When you put the principles side by side, the parallels are just undeniable. Both systems navigate these complex energy landscapes. Both of them form clusters to be more efficient, and both can adapt and reorganize themselves when things change. It's like they're singing from the same hymn sheet.
And this is the moment it all just clicks into place. Get this. Real mitochondria in our cells tend to form clusters of 4 to 8. And what did the best, most organized quantum simulation produce? 6 clusters. It's a direct numerical match, popping up from two worlds that seem like they have nothing to do with each other. It seems they're both just following the most efficient path laid out by the laws of physics.
So here's the takeaway. Divot theory is suggesting that evolution isn't just a brilliant inventor, it's also a brilliant opportunist. It didn't have to figure out the super complex rules of organization from scratch. The rules were already there, baked into the quantum fabric of the universe. Life just learned how to use them.
You know, understanding this deep connection isn't just a cool piece of science. It has profound implications for the future. It's opening up entirely new ways of thinking about technology, medicine, you name it. I mean, if we really understand the universe's natural organizing principles, we can start using them. We could design quantum computers with more stable qubits. We could develop brand new therapies for mitochondrial diseases just by understanding their network structure, create materials that literally build themselves, and design vastly more efficient energy systems, all by following nature's own quantum blueprint.
Which leaves us with one final, just mind-blowing thought to chew on. We found this connection in the powerhouse of the cell. But if the fundamental blueprint for complex, lifelike organization is written into the very laws of quantum mechanics, what else have we been looking at our whole lives without even realizing it was built on that exact same foundation?